All right, so today, actually, I want to talk about a subject which is, once again, very interesting for me personally, which is the strut and tie modeling, because it provides a physical and graphical and conceptual understanding of the structures in contrast to numerical methods, which sometimes do not actually give us a clear idea what's happening to the structure itself. So now, as always, I would like to start with a historical perspective for structural application in strut and tie. So if you look at the old structures, historical, most of the structures you will find that they have a common feature, which is either an arch or a dome or vaults. And all of these are based on the concept of the thrust flow into the structure in such a way that the load applied to a structure flows through the structure within the structure's boundaries, goes to the foundations. And that has been always the way that the ancient architects, you can call them designers, engineers, or builders, have worked. And they took great effort in ensuring that the force flow is within the structure. And that's why you see all these great structures of the same form, especially in most of the historical buildings. And then thin shells became a specialty later because thin shells form was specially optimized and configured in such a way that no matter what, even though the thickness is very thin, it will always be in compression, or even if it is tension, it is within the thickness of the structure. And this was a great art and understanding on how to make sure that we design a structure which will not have any transverse bending, but rather in-plane forces, just like an arch or a dome. Only this time it was extremely thin. So paraboloid, hyperbolic paraboloids and things like that became very popular. Nervy and many people started to use them when concrete became available. And so this was the basic concept: force flow. If it's a column, straight force flows through the column to the foundation. Arch, the same thing, and cable, the same thing. So these three forms, these three structures were used in history for a long time. And then one of the person, Hooke, he found this very interesting principle that if you hang a chain or hang a cable, whatever form it creates, if you reverse it, then you will have an arch which will have the force flowing through it in compression, because the cable form is showing you the tension flowing through the form. So this was a great way to create the thrust lines in structures in compression, which otherwise might be difficult. So they will use this concept of hanging chain or hanging cable, reversing the form to find the thrust line and design the structures accordingly. So this is one of the interesting things that they found, and that's a lot of the arches later. A lot of these thin shells actually became fabric structures, which were reversed in form after hanging them down, and then they reverse it, and it became a thin shell. And I think we all know the story about the egg, where if you try to break it on a certain angle, you just can't. And there's a picture showing an elephant standing on an egg without breaking it, because it flows through the skin. But the problem started when the structures became flat, and then the force flow, the thrust line did not go to the supports. It stopped midway. And then at that time, people did not understand how to design a structure where the thrust line is not following from the load to the support. And this is the start of the problem in engineering. And then this guy, Galileo, he is the one, before that, actually, Da Vinci also, but Galileo tried to solve this problem of the cantilever, and he developed some understanding which was not entirely correct, but he started to see that, okay, if you apply the load at this point, at the other end of the cantilever, there'll be certain stresses generated, and he tried to develop the theory at that time. But that's the formal start of the structural mechanics, you might call it. And then there's a long history of people who worked on this problem, starting from Da Vinci, who, as you know, architect, builder, everything, artist, he wanted to make many things. And then later Galileo, and then Robert Hooke, as you showed, and then Bernoulli, and then two Bernoullis, and then we have the Euler, and then Kochi, and Timoshenko. So most of them you already heard, and they all contributed over a period of 400 or 500 years to develop the understanding of the beam theory gradually. So it took hundreds of years before we understood what's going on in a beam. And these two, especially principles, are very important. One is the plane section remain plane after bending, after Bernoulli and Euler. And the second one is the Saint-Bernard principle, which is talking about the local disturbances, whereas the left on the side is talking about the general deformations in a beam. But he said that, no, close to the support, close to the points, there's a local disturbance, which alters the plane section remain plane bending concept. And so this became another important discovery. So these two discoveries together then went ahead to develop most of what we know about the beam design. So important thing that was discovered was the deformation controlling the deformation, or the dominant deformation was actually a summation of the flexural deformation plus the shear deformation. And it was found that when the member or the beam has a long span, or the length over height ratio is long, then primarily the flexural deformations govern. And when the beam becomes very short, the flexural deformations become insignificant, stiffness becomes very large, and if there is any deformation, it mostly comes from shear. So very small beams of small length, almost entirely the deformation is contributed by shear deformation, and the flexural, so that means there's no bending, the load transfer is through shear. And that was an interesting finding that led to further changes. So that's what we are. So that's the kind of a summary of the difference between the plane section remain plane and the plane section not remaining plane in that area. So let's get back to the difference between beam or a truss, because truss was known earlier than beam in terms of the strut and tie. So if you look at the truss, and if you, let's say you want to transfer this load and you orient the truss in a certain direction, you will get the forces according to that. So you will get, but if you orient the truss reverse, opposite direction, you will still get the forces, because you are still trying to transfer the force through tension and compression. Only the directions will be changed. One is efficient, another one is not. It all depends on how we look at it. But if you look at that, you will get the forces in this way, and the other one, you will get the forces in this way. So depending on how you transfer the last force, the one on the left is a preferred approach, where we transfer the diagonal in compression, vertical in tension, and there are many reasons behind that, and then the bottom is the tension. So this idea of the truss has been used quite a lot, and people found that the one on the left generally works better. And especially moving forward, we will see why. Now let's get back to the beam. So if that's a beam, now the thing is that when you design the truss, for example, here, it's very simple. You apply the load using the simple statics or calculation. You can calculate the forces in the diagonals, also on the top and bottom chord. We all have done it in an undergraduate using whatever method. So there's no, and directly from the force, you can calculate the size of the member or check the member capacity. But in a beam, we go slightly differently. We take the beam, first we calculate bending moment, then we calculate shear force, then we go back to the section, then we try to convert that bending moment and shear forces, for example, back into stresses, and try to do all calculation, ignoring the tension and whatever, and then we try to compute the internal moment capacity, equate it with the external moment, and that is the short form, and this is the long form of internal equilibrium, comprehensive case of internal stresses in equilibrium with external moments on, you have the stress resultant. So in either case, whatever we use, first or the second equation, we are able to determine the capacity, but we kind of go the long way in this way. But the truss is straightforward. But now look at the beam design calculation here on that side. You will see that there's a lot of calculation involved in just a simple beam. So many equations, so many checks, so many things, 16 pages of calculation just to get the reinforcement in this beam correctly, both shear and that one, whereas the truss maybe will take half a page to do the same thing. So we are complicating certain thing. There's a reason behind that, but that's how it works. So but if you come back to the truss again, or the beam, and then you look at the beam more closely, actually it's no different from a truss, because the concrete here is behaving like strut between the ties, and the bottom reinforcement becomes the tie, vertical reinforcement ties ties become ties, and then you actually end up a hidden truss within a beam. So really speaking, it's not much different from what we were doing in the truss, only we are doing it in a slightly more elaborate way for multiple reasons. But let's just look at this first, that the beam is no different from the truss in terms of the internal mechanics, especially for the shear. And in fact, if you calculate a beam using the long formula for the beam theory, and you calculate the size of the reinforcement or the size of the member at the bottom, you will find that the two give almost the same answer. Left-hand side, you'd use the beam theory. Right-hand side, you use the truss analysis, and one is giving you 305, another one 297. Actually, you should correct the thickness, the height a little bit, because the truss will be slightly smaller because of the location of the reinforcement. So you'll probably end up with the same results. So you can see that even now, the reinforcement in a beam generally can be estimated as if it is a truss with just dividing the moment by the lever arm. And same is very much true for the shear as well, because shear is anyway based on the truss concept. Now look at this poor beam. This is subjected to axial load, torsion, bending moment, and shear, and probably double moment and double shear can also be done in a typical 3D element. So if you have a beam like this, and there's an element at the face of this beam, you will see that that element is undergoing many stresses. So here's a simplified version of that. So you have axial stresses coming from axial load, tension, or compression. You have shear stresses coming from shear. You have axial stresses coming from bending moment at the top, at the bottom. You have shear stresses coming from torsion, both direction. So basically, everywhere on the beam, there are axial stresses and there are shear stresses coming from bending moment, axial force, shear force, and torsion. But ultimately, there are just two stresses left. Either it's a shear or it's an axial force. And it is either going to cause a compression or a tension in that element that is there. So that's what is happening in a shallow beam, even forget about the deep beam. So if you look at the stress, now if you look at the axial stresses and the shear stresses, and if you then use the principle like this, you transform them, then you will get a plane on which the shear stress and by transformation, you can calculate the principal stresses, or you can calculate stresses resultants on any plane based on that one. And those can be given here. And then from that, you can rotate it in such a way that you get a plane on which the shear stress is 0, and you only left with tension and one maximum axial and minimum axial stresses, as you know, called principal stresses. So I'm just reviewing the undergraduate work for you. And the good old Mohr circle is used to do that. So basically, from the shear stresses and axial stresses, we can get principal stresses, max and min. One is tension, one is compression, and that's all there is left for it. Everything else is now gone. So this was first recognized in the design of torsion for beams. Those of you who are as old as I am may remember that torsion design of beam used to be extremely complicated earlier in the codes when they tried to account for the stress pattern using the traditional method. But later they realized that this is not necessary, and it was simplified, and the space stress model was introduced in the codes, which says that torsion produces just stresses around that. And if you decompose them into principal stresses, then you're left with tension compression. And based on that, you can then create a space truss around the beam and then design that. And the rest of the beam in the middle is doing nothing, and that can just be taken out. So that's greatly simplified the torsion design of beams a few years back or a few decades back. And now we have a very simple way to design the beam for torsion using this space truss concept. So if you look at actually the four faces of the beam and then you plot the principal stresses from torsion on each one of them, you will find that they have different signs, but different because of the shear stress on torsion on opposite sides is of the opposite sign. And then you get these struts, compression struts and ties. And then you put them together and you just get the space truss. This greatly simplified the design of the beams for torsion and also for shear. The same concept is used. So it's nothing new. We are already using the concept of the strut and tie in a way in concrete design, even for shallow ones. So you get the complete picture now. And then you also get axial stresses and axial reinforcement increase because of the truss mechanism. You have AL, or the axial reinforcement increase because due to torsion coming from the truss mechanism. So we can conclude now that it's all about compression and tension. So we just have to follow the principal stresses. And that's the lesson. That's what we are going to do now. So axial stresses is the end point. Axial stress is either tension or compression. Axial stresses may be due to direct axial load, bending moments, torsion, or from shear, and from torsion, shear converted back into axial at the principal direction. So that's what we have now. And we can see from here that if you take a beam and do the shell analysis for this beam using SAP or whatever program you like, and you ask SAP to plot the principal direction of stresses, look at that. It shows very clearly that there is a compression going that way, and there's a tension below that. So it's so obvious looking at these principal direction of stresses provided by a shell element of analysis. Same thing we can do for beams with more, different lengths and different heights. So you can see that there are multiple being formed. You can go even further. You can do like that. You can even look at the direction in more complicated structures. So basically what I'm saying is that we can follow the stress trajectories to find what the direction of the force flow is. So that's the internal force flow. And that is the most efficient way to design the section, because that's where the structure wants to go. So elastic stresses are indicating to you the intent of the structure to resist the external forces. So if you follow them closely, you will end up with a structure which will have minimal problem with cracking and all, because we are trying to control the stresses in a way that the structure is trying to create them. So we are just posing them in the same way rather than an arbitrary way of assuming internal stress mechanism. Just some people try to do that to the extreme. They said, okay, why don't we try to follow the stresses in this great bridge? And this is what they come up with as a stress flow. So that is a very valid stress flow, although impractical in many ways. But that's how, if you put a beam of that size and let it follow the stresses, you will probably get a structure of this kind. So let's formalize now the strut and tie modeling based on all the things that we have said so far. And once again, these are the people who helped develop it. So this started same time as Hooke, because he gave the idea of the reversing thing with tension and compression. But the people who really made it possible was the Leonhardt from Germany, and later Schleich. These two people, both from Germany, they really brought this idea back from the old days and revive it. Because once the beam theory was developed sufficiently, people thought that this strut and tie is old method. This is not, we should follow the newly acquired knowledge and the mathematics. But these gentlemen said that no, this is still very good. And based on their work, later, Collins and other Mitchell, they also put it in their books. And then we have the ACI follow it. See, it's so interesting. First, ACI put it in 1999 as an appendix, very, like a reluctantly, just thinking, and now it's part of the main code. Now it's part of every main code. In fact, strut and tie is gaining more popularity even in nonlinear analysis, which we will see later. So going back now, a typical beam with a point load with these three parameters, A, D, and L. These are the three controlling parameters which determine whether the strut and tie method, how it will work, how efficient it is, when we should use it, when we should not use it. And there are a lot of formulas on will tell you what should be the ratio of A over D over A over L, D over L, L over D, when when this is more efficient. So in general, it's very efficient when the beam is not primarily in a bending mode, as I showed you earlier, when the deformations are primarily controlled by shear. Then this strut and tie model works best. Of course, it even works for ordinary beams, as I've shown you earlier. So this is now a stress trajectories plot, and you can see they have identified interesting regions. there is a D region on the left-hand side, then there's a B region in the middle, then there's another D region, another D region, another D region. So D region is where as you can see, the stresses at the top and bottom are not parallel. They are going, so which means the plane section does not remain plane in that area. And that is everywhere there's a disturbance, according to Saint-Venant principle. Everywhere there's a disturbance which is close to the support or close to a point load, then you will have the disturbed region, which is typically equal to the depth of the member. So we can see here that most of this beam is in D region now, and only small portion is in B region. So the D region, bending theory, plane section remain plane, does not hold true, and the force transfer will be primarily through strut and tie mechanism, through principal stress directions and so on, because bending isn't there, it's all about shear. So that's the kind of thing, and then you can find this more elaborate in this manner. So almost every structure has a D and B region, and if you go further, you can see even in most of the places around the openings, around the concentrated loads, around the supports, you find these D regions everywhere. So wherever there's a D region, that is where the strut and tie is applicable more. In B region also you can use it, but it's more useful or more efficient or more, I would say, prudent to use wherever you find a D region. Again, D regions in everywhere, in brackets, in footings, in supports, under the loads and the openings, every change in section. Wherever there is a discontinuity, there is a disturbance, you have a D region, and you have an opportunity to use the strut and tie approach. It just shows that when you have a beam, and when you change the span, it will, the struts will follow the span. Yeah. And then it keeps on going until a time comes where the strut angle becomes too shallow, and then you may have to create a secondary load transfer mechanism. That means that the first diagonal will not reach the support, so you need to carry this load back up, and second strut will bring it down. That's the principle. If you draw this thrust line roughly at 45 degrees angle, between 35 to 60 degrees, and if it doesn't hit the support, you need to carry it back up the top and bring it back again. Every time you carry it up, you need ties or reinforcement or tension, and those are the stirrups that you have in beams. So if you do not need to carry the load up back, you do not need the stirrups. That's the idea. And of course, the tension is very clear. So that's what we are doing here. And this is shown by this diagram a little bit more clearly. So as the length increases, you have this zone of acceptability, which is somewhere between 65 degree angles to 35 degree angle. Within that, if your thrust line is within that, you can just design it for compression. No need to design it for shear because there is no shear. And then you put the tension here. And you'll need to only put the tension if the supports are movable. If the supports are immovable, it's actually, you just take the load to the supports, won't be any tension, but practically you don't have immovable supports. And then you can see here the green area is both can be done. Blue is where you need to do that. So what we conclude from this one is that for L over D less than 4, you can use the strut and tie directly. With LD over 4, auxiliary trusses as needed. LD over 5, beam tends to behave in an ordinary flexural manner, and you can use the ordinary theory. So that's just roughly what you can observe from here. Another thing is how many verticals you should use. So 45 is most preferred and assumed and efficient. In fact, 34 degrees is the most efficient, but it's a little bit more difficult to use. So 45 degrees is what you will want to use. But in a beam, actually, it doesn't matter, because no matter how many times you use this vertical, you have to divide it by the spacing. So you end up with the same kind of reinforcement. But if you want to make a steel truss, it will be highly uneconomical to use the one at the bottom. Most economical will be around between 30 to 50 degrees. So once again, a small animation to show you the same thing. So these forces go to the end is too flat. So this is not good. So which means that you actually need to draw the line at an angle of 45 degrees. And when you draw the angle, you reach the bottom, you take it up, you bring it down. That's how the strut and tie is supposed to work. And this is the efficient way to do that. And then if you want, you can actually do more. You can bring it back at its steeper angle, take up, take down, still did not reach the support, take it up again, bring it back to the support again. So this is another one, 45 degrees. And the next one will be more inefficient because it will give you more angles. So to conclude now, strut and tie method in a unified approach is that you can design it for moment, axial force, shear, and torsion. Only one model is sufficient. We don't need a separate flexural theory, a shear theory, and a torsion theory. All of this can be handled by a single model. That's the beauty of the strut and tie approach. It has evolved, and it's evolving to especially apply for structures with predominant D regions. There is no single unique STM. That's the beauty of this. You can create multiple models, and most efficient will be the one that we should be using. Some will be valid, some invalid, but multiple ways load can be transferred that you can conceive. And then this is just the basic principle that I have already mentioned. I don't need to repeat that. The main thing is here. So in the application of the strut and tie approach, the section is assumed to be fully cracked. That means we are assuming that concrete takes no tension. All tension is taken by ties, and all compression is taken by struts. And ties and struts provide a stable mechanism, and it's a lower bound solution. Why is it a lower bound solution? It's a safe solution because we are ignoring all of the tension carried by concrete, which is substantial. Major part of the section is still uncracked. So we are not taking into account the contribution of that section. So it's a safer bet in a way. So it's a lower bound solution to the problem. And it's always going to be safe as long as the equilibrium is satisfied. We use it when the stress flow is greatly influenced by shear or torsion, as I mentioned to you earlier. And then the physical dimension, load application, and support locations are clearly defined. And we will see in a few minutes that the size of the supports, size of the members actually matters. There is no such thing as a point load in a real structure. There's no such thing as a pin support or a knife edge support in real structures. Supports have finite dimensions. Loadings have finite dimensions, and that affects the stress flow and the strut and tie models. So this is a basic strut and tie model. We have the struts, we have the ties, and we have the nodes or the joints. Just like any steel truss, you will have the tension members, you'll have the compression members, and then you will have connections by plates or bolting or welding or whatever. So, and the stability of the truss depends on the stability of the connections. The same is true for strut and tie model. It cannot be automatically assumed that when you form the strut and ties, it will work. We need to make sure that the connections or the joints will also work. So there's three things to be checked: the ties, the struts, and the nodal zones or the joint portions. So struts, compression members, in concrete, strut can crush or buckle. So we have to check for those. It's just like a column. Tie is a tension member, reinforcement. Tie could yield, so we have to prevent it from yielding, and also from anchorage problem, which I will mention, as you can see from the figure, and anchorage is very important. Node is a connection, is concrete portion. Node could fail in compression or in shear. So this is the summary of how a truss should be, strut and tie model should be conceived, analyzed, designed, verified. Strut, through the strut, just like a column, the stresses will flow. And if it is a strut is uniform, it will just flow like that. But if it is a bottle-shaped truss, then the truss may have fans. It may spread out. And similarly, we have fan-shaped struts. So depending upon the size of the support, depending upon the size of the loading, depending upon many parameters of the physics of the structure, these struts could be prismatic, bottled, or fan. And almost no no strut will be prismatic because the structure is not confined like that. And the struts will have another form. So you can see here that even if you assume the strut to be like this one, in reality, the strut will be a bottle-shaped truss because the stress, based on the principle of Saint-Venant, the stress will gradually spread and become uniform, not just go uniform all the way. It will converge to the support and then spread out and then become like that. So that's very important to note that it will happen. And as you can see, when that happens, when the stress is spread, the angle will change. And when the angle will change, internal substrutting or substructures will form. Ties and struts will form within a strut to prevent that diagonal, that crack that you see, which is going to be just like a cylinder. When you test it and you apply axial load, it splits on the sideways because of the Poisson's ratio. The same thing will happen here, and also the stresses are going at an angle. So in the middle, you will expect a crack in the strut, and to prevent that, secondary reinforcement may be needed, just like a column confinement may be needed. So think of the strut as a column within a structure. Generally, this will be small, but for very heavy loads, this could be a problem, and this should be checked. So struts can fail just like columns. They can fail in compression, they can buckle, they can crack, they can bust. If let's say it's a deep beam, it's very narrow, then they can bust out or they can buckle. And then we limit the KL/R ratio just like columns. So whatever the column can happen to a column, same can happen to a strut. Tension ties, the main problem with the tension ties is the anchorage, because in this case, you can see here that the development length available for the ties is very small. Unless we take special care, this small length within the joint, it must develop within the size of the joint, which depends on the size of the support. And so that means the tie needs to be, the diameters of the ties or rebars has to be such that they can develop. So normally smaller diameter bars, more diameter bars distributed will be better than a few large bars, or sometimes people use plate at the end, sometimes they bend it up and so on. So this anchorage of the ties is very critical to make sure that they anchor within the joint zone. So for the ties, we can assume larger bars on the corners, assume more bars on the predominant tension areas, assume uniform reinforcement on beam sides. So this is the way, and typically we limit the ratio not to be more than this rate, 0.8 to 3%. Is also too high. About less than 2% is what we should assume within the tie zone, not the whole member. So coming back to the nodes or the joints, there are of these primary types, 4 primary types: CCC, where we have 3 compressions meeting at one point. We have CCT, 2 compressions, 1 tension; CTT, 1 compression, 2 tensions; and TTT, 3 tensions. Most common are CCT and CCC. Others are less common. They can develop in certain cases, but not very common. So most common you will see is CCC and CCT that we need to deal with. So this is a little bit more detailed how a typical connection will look like. And then you can see from here that when the forces come on a point, the black portion is the joint portion or the node portion. And it depends on the sizes of these struts coming in there, or sizes of the ties coming in there. And it depends on the size of the support, because it starts from the size of the support and starts from the size of the loading plate. Because like I said, there's nothing as a point load. So if you want to reduce the stresses in the joint or want to make the node larger, we spread the load to a larger portion. So the joint becomes, the strut dimension becomes larger, the joint becomes larger, and we can reduce the stresses. And that's one way to manage the nodes, is by increasing. At the bottom, you can see that the tension is difficult to develop within the small size of the node. So the member is extended a little bit so that the bars can be extended to develop. Or in the upper case, you can see the plate has been added and bolts have been added to mechanically anchor the rebars. So this is very critical, that the reinforcement is fully anchored in the nodes. Then we have two types of nodes, the hydrostatic and non-hydrostatic. So hydrostatic are the ones which are completely confined by the size of the member, and the non-hydrostatic are where they are not completely facing the support size. So that means supports size on one end or the other two end is not the same, or we have the sizes which the inclination is such that it doesn't match with the size of the support. So that's why 45-degree angles are the best, and that's why the size of the support matters to keep the nodes hydrostatic. Hydrostatic nodes are the best because it's a fully confined zone and you don't have a leakage of stresses. Then there is a correct and incorrect strut and tie model. For example, the one on the left is also possible. You can tie the load up and carry it down, but it's just not the way the concrete will want to behave. Concrete will want to behave based on the one on the right, which is the compression down and tension at the bottom. So that's why I mentioned that the initial strut and tie should be derived from the elastic analysis and principal direction of the stresses. Compression, principal stress leading to the struts, and tension, principal stresses leading to the ties. Then you will get a good starting point. Otherwise, you will get a strut which will crack, or you'll get a model which will not be efficient. So obviously, like anything that we have, there are drawbacks to this approach. Number one, it only guarantees stability and strength, doesn't have any direct checks on serviceability. Then inappropriate assumed truss layout may cause excessive cracking, like I showed you. If you do not size and orient the trusses well, then you can have cracking. And it requires experience and judgment in truss layout, member size assumption, result interpretation, and rebar distribution, because it's physical. So you need, it's not something like a model that you make in software and it will always give you some answers, right or wrong. Here, you have to start with the correct understanding of the force flow and take it all the way from the initial concept to rebar detailing. So let's look at some applications now. So first one is the deep beams and transfer girders, which is the most common application of these strut and tie models. And like I said, I'm not going to go into too much detail. We can have separate sessions on each of these topics. This slide I borrowed from Professor Bhupinder from IIT Roorkee. He was very kind enough to share this with me. One of the tests that they did in the lab, where you can see the crushing and the failure of a deep narrow beam, and this formation of the struts and the crack between that. So this is a deep beam board failure, which, as you can see, is different from the other beams failure. And this is the load transfer mechanism. So once again, when you have the struts doesn't have to be the incorrect strut and the correct struts. They're different shapes shown here. And the struts can be subdivided into smaller portion. If you, and what we're showing here is that if you increase the reinforcement distribution at the bottom and increase the size of that area of that band, then basically you are trying to make sure that your joint is big enough, you have smaller diameter bars, and you're spread around, the cracking will be prevented, and so on. So secondary trussing or minor trusses can also be used. And then the idea that within each strut, there is a sub-strut which should also be prevented from cracking. So this is a typical problem in a deep beam or the transfer girder type structures. Another thing that happens in a deep beam or a transfer girder is the formation of the arch. And it only forms, as you can see here, so it's trying to form an arch by itself. So it's similar to a strut and tie, but it's more like a tied arch. And it's so whether you have a strut, you have a truss, or you're in a tied arch, their behavior is quite similar. The only thing is that you can see from the patterns that you can connect them through a strut, or you can assume it to be an arch, tied arch. End result is nearly the same. So these are two internal mechanisms that you could think of when interpreting the internal stresses and the crack patterns. So this is a most famous building with the transfer girder here, with several columns stopping at the top. with a deep girder, two, 3-story deep girder, and then multiple point loads on it. And many people have cited that one. Here also the same thing, and other buildings of this kind. So if you have a transfer girder, then you can see that you can create a strut and tie. Several models are possible here. And this is just one model. And then you can analyze these models. And then many buildings, architects prefer to actually show these trusses directly in steel or in concrete because it looks very nice to actually transfer the load by direct inclined struts or columns and make a truss there with a space open with the glass or whatever. So many buildings tend to do that also because you really don't need the concrete between the triangles. And once again, the transfer girder stresses can be checked by finite element analysis, and then this can be used as a guideline. Another one, very common application is the pile caps, because pile caps are very large structures, deep but small, with large loading, large sizes of the supports as well as columns. So pile caps were designed as simpler flexion members, which doesn't work, and it was used a long time. Beam slab, all of these doesn't give good results. The tie and strut model is most preferred by bridge engineers and many engineers who design pile caps, although footing approach or the deep beam approach or bracket design approach also has been used. But as you can see here, that strut and tie is more clear. But I want to emphasize one thing here, very important. If you look at the figure on the left-hand side, where a simple truss model is used, that means you have only 3 members, 2 struts and 1 tie, and then you assume that the whole big column load is a point load, then you get this very simple truss. The problem with this one, first of all, if you have a bending moment on the column, you cannot apply that bending moment to this truss because truss by definition doesn't have the moment degree of freedom. So the bending moment from the column cannot be transferred through this mechanism. That's problem number one. The second problem is if the column is small or large, this will always give you the same forces, which is not true. But if you modify the truss on the right-hand side and you move the joint towards close to the end of the column, assuming that the column is also kind of a truss with the tension and compression sides, which is true, and then you create the truss like that, now you have the ability to apply bending moment to this column also because it will be converted into 2 pair of forces on the nodes. And then as the column size changes, the truss model will change and the forces will change, giving you much realistic and efficient way. And just to demonstrate below, you can see that if you use the first model, you get tension equal to 4,500. If you use the second model, you get tension equal to 1,900, half. So that means the reinforcement, the bottom of the pile cap can be half that of the assumption of a point load and in a simple truss. And this is very important. The second important point that to note on this one is the supports. You cannot or should never use a pin-pin support on a truss model, because if you do that, then you will never get any tension because the pin-pin support will just absorb the strut forces, giving the horizontal reaction, and you will get zero tension. And this is a mistake that many engineers have made. So the support should be either pin roller or spring kind of a support. So they are allowed to let the truss deform and give the forces properly. But in reality, this is actually 2D view of that. But in reality, this is a 3-dimensional structure. So there's a column, there are 4 piles, not 2. So in fact, inside the volume of the pile cap of 4 trusses will form, and the column's corners will become 4 point loads on that one. And 4 piles will become 4 supports, spring supports at the bottom. And then this will be the right true force transfer mechanism within the solid of the pile cap. And if you do that, then you will get much better results because you capture the 3-dimensionality and the size of the column and the 2 bending moments and everything properly. Even torsion or shear can also be applied to this model easily. So that's the way that the space stress model for pile cap can be used. So it's just showing you the same thing in a little bit conceptual manner. When you have load this one, you have the load goes to the 4 piles through that one, forming kind of a cone, and the rest, and then that is converted to a strut and tie model. And then you can analyze that space stress, and then you will get the forces, and then you can design that. And then you can expand that to 6 pile case or more. This is a model, space stress model of a 6 pile, 2 column pile cap from a big bridge. And you can see basic model, forces, compression forces, and the tensile forces. It's important to see that the model below, the one just below the loading, is using pin support. And you can see 0 tension. There are no ties here. There is no tension. That means if you replace the piles by pin support on all locations, you will not get any tension because the supports will just absorb the strut forces. And that is so wrong because you will not have any reinforcement in the pile cap then. So we need to make sure that we use pin roller or we use spring supports appropriately. And then you can expand that to 5 piles, 3 piles, 12 piles, whatever case. So it can easily be expanded to cover more complicated configurations of the pile cap, not just the 4 pile cap on the single column case. So this is a major application of the space truss models, as you can see from here. Another application is link beams in tall buildings, especially for earthquakes, corbels, brackets, and joints. That is the concrete portion within the small portions that normally we just do not even think about. So that's the stresses in a corbel. So when you have a bracket or a corbel, the stresses are highly concentrated. It's a shear mode. There's no bending because of the depth to point A over D ratios are so small. So you can see from here that based on this stress distribution, you can determine the strut and tie directions and locations. And this is a typical mechanism to handle a bracket using the strut and tie. So you have the diagonal struts there, and then you have tie at the top. And of course, shear friction and other things need to be checked as separate one, but the basic mechanism tends to be of this kind. And this is the most common way to design brackets. And then we have a shear plane for which the shear friction could be checked on top of that. Joints. So joints, especially for seismic loading, where the direction of the moment is both positive on both sides, will produce the diagonal forces on the connection. If you have a gravity load on a joint, then it doesn't matter because you have tension at the top and bottom and compression at the bottom passing through the joint. But if you have moment from the earthquake, one is this way, one is this way, both of them in this way, that means they will produce diagonal shear or shear in the joint. And that shear is in a very confined portion, which is the A over D is equal to 1 roughly. So it will purely be a strut and tie. One direction will be strut, one direction will be tie. And that's how the joints are designed in shear by calculating simplifying that into strut and tie model. So strut and tie, one in this direction, one in this direction. And then you end up with a strut and tie model. Half joints, the same thing. If you have a half joint in a girder or a beam resting on that one, once again, the load transfer can be done by the struts, as I mentioned, go up, go down, go up, go down. All the loads are transferred, and then internal strut mechanism is used to do that. So especially strut and tie model is extremely useful for very large structures, but also very useful in the joint portions, which have complicated stresses and there's no concept of plane sections in there. Obviously, it's all a D region. So if that is a D region, then we should resort to strut and tie models. Another one is floor diaphragm. And this is a relatively new topic in the sense that the design of the floor diaphragm, especially in tall buildings, has not been very common. It has become to design practice recently. So floor diaphragms, let's look at that a little bit. So if you look at the earthquake flowing through a floor, this is a kind of an ideal case where you have the framing outside and the floor is flexible floor. And then if this force will flow through because of the masses here from earthquake, there's no force as such. The force is being generated locally by the slab through inertia. So the total will be an equivalent force that we have represented by EQ, but actually there's no applied force like that. So that those forces which are being generated then create this zone of compression this way, and they will transfer to the side walls or to the supporting structure. This is an idealized case. I will go to more real cases in a minute. And then you can have a kind of a compression system forming and a tie forming at the bottom. So this becomes the internal force transfer mechanism within the diaphragm, large diaphragm with compression and tension. And then that portion will be in tension. So to prevent this portion from splitting down, we can tie it back, sometimes called as the collectors, and tie it back to the compression. So it's not only the horizontal, but also the vertical lines are also needed to keep that yellow portion from moving away. So that's the rough representation of a floor diaphragm using the strut and tie when the floor diaphragm is just transferring the load within the diaphragm. And this is common for precast floors or steel with a very thin deck. Reinforced concrete floors with a lot of reinforcement, probably this will be automatically handled. But it may be a problem when we use precast panels or using steel decking and so on. So you have to explicitly check for this transfer. But the real problem for the floor diaphragm actually comes in tall buildings, where suddenly the large forces from the core wall, from the tower, have to be transferred to the podiums at certain level. And here the podiums may have large stiffness. And so before the load can transfer, shear can transfer from the wall to the foundation, the podium floors will intercept it and try to spread it around. And that's where the large force transfer will occur in the floor diaphragms, especially in the podiums or even in the basements. And this is a complicated stuff, and many methods have been developed to do that. Strut and tie is one of them. There's a traditional methods of section cuts and collectors and so on. So maybe we will have time to discuss this another time. This is an interesting real project that we did here. It's a project in Philippines. So there are 3 towers here on this podium. And the problem is that these towers will be built at a different time. One tower now, another tower in 5 years from there, another one. That means the diaphragm is built first, the podium is built first, but the towers aren't there. So during that time, if the earthquake comes, we have different ways that the load can transfer. And the core walls in the podium are already built, but the tower is not built. So which means that intermediately, you have to consider many scenarios for the load transfer from the completed tower to the unfinished. And then when all towers are complete, then the towers may be moving in different direction because of their orientation. So at different time interval and also at different earthquakes, they may be moving in different directions, opposite. So causing shear, axial forces, bending moment in the podium. So it's a very complicated scenario in which several directions of forces need to be considered. And here, once again, the basic concept could be strut and tie, but detailed design will need finite element analysis as well. So one approach that people are using now is the grillage truss model. That means they divide the floor into large number of trusses and let the forces flow through these trusses and find the forces. It's just like what we did in the beam. You instead of using the shell element and then trying to find the principal directions, we prefix the direction using the truss elements and then simply find the forces in the diagonal trusses and then design the reinforcement and compress stresses based on the forces we find in this one. Some portion will have no stresses, some will have stresses. So this is one way people are working. There are a couple of very good papers on this. In fact, a whole software has been developed on top of ETABS that does this work. So this has been applied, this adaptive analysis tool. So which is called auto diaphragm, and this basically takes the floor and subdivides it into thousands upon thousands small trusses, and then let the earthquake ground motions analysis run on this mesh and simply pick up the forces, tension or compression in the truss elements, and then design the reinforcement locally. And the advantage is that the local stress concentrations and local trusses, local struts can be picked up. This is better than using the section cut process because section cut assumes a certain direction of forces. And if the forces are in the other direction, section cut may miss it. So this approach has the advantage that it tries to follow the natural force flow. Like I mentioned, it's the way that we are talking about to try to follow the natural force flow or stress flow within the diaphragm, especially with openings and core walls and discontinuities. So this is a good approach in this direction. This is another document that most people use, which is quite a good document for, especially for tall building. But this uses the cords and collector method. But within that document, they also have a strut and tie alternative also, where they say that around the opening, you can find a strut and tie mechanism and design accordingly together with the collectors. The collectors are basically to bring collect the force or the stresses to the struts and ties, because struts and ties cannot, they cannot, because a continuum, they cannot just exist and come out of existence suddenly. They need to spread around, and that spread around portion is done by the collectors. So that's how the floor diaphragms can be modeled, multiple ways. Let's look at some other applications quickly. Bridge bends, a lot of application is there. People are doing a lot, especially post-tension bridges and all. So you can always, because it's ideally suited because the girders are point loads, perfectly located, the direction is clear, and the structure is large. So strut and tie is very useful for bridge bend analysis and design. Another one is the masonry infill walls. And this is a topic which many engineers choose to ignore the masonry infill walls in their models. They think it doesn't exist, and they create a bare frame and analyze. But masonry infill, especially in subcontinent, where they are quite thick, quite large, they have a lot of stiffness, and they have a lot of contribution to the behavior of the structure. Both modal response is affected, linear, nonlinear, both are affected. So incorporating the masonry walls in the model is rather important. And the most easy way is to use the strut concept. That means you replace the masonry wall by equivalent strut, because masonry wall is a shear element, and strut is basically taking shear. As we have seen, wherever there is a shear dominant behavior, strut is the solution. So because wall is a shear dominant structure, so strut is the solution. And then you can replace that by the strut. As you can see here, placement of the strut could be at the corner, could the bottom of the column, or there could be multiple struts going around the opening. So these are some of the ways that the struts can be used to model the masonry walls, not only for linear, but also for nonlinear analysis. So FEMA gives very good, ASC 41 and FEMA both give very good equations to calculate the strut stiffnesses, and linear, nonlinear both. And then SAP, you can model them, or ETABS, you can model them as members with tension and compression limits. And these limits are extremely important because these struts are not infinite. So they must have the capacity to break or not participate in the load carrying. So tension limit and compression limits should be calculated and put as a data. And then use these struts as tension compression controlled elements. And that way you can capture the true behavior of the wall, which in the beginning is acting as a strut. At some point it breaks and becomes disconnected and doesn't take any tension. So it's a very nice, neat way to represent the global behavior of the wall. So this is, for example, a building, a small school building in Philippines. where the struts are used everywhere to represent the wall. So without that, this building's seismic response will not be reliable. And then the good thing is that you can make these struts nonlinear. And then you can use them in pushover and time history analysis to actually determine their failure points and their contribution. And then you can say, okay, which wall will break, which will not break, which will go to which level of performance. And that's the good thing about using the masonry infill walls as nonlinear elements or struts in a nonlinear dynamic analysis, because they give you the ability to predict which walls will be breaking at what level of earthquake and so on. So this is a good tool to do that. And here, shear walls can be also represented by strut and ties. And once again, you can do a nonlinear analysis of the shear wall by using the nonlinear struts. This is what we used to do before, more sophisticated methods of wall, like the shell or the other methods came into being. You could just convert the wall into an equivalent truss model. Deep beams, girders, if you want to do nonlinear analysis, then of course there are several ways. You cannot use a frame element for the deep beam, as we already know. You could use a layered shell element in SAP to model the girder as a shell model with a nonlinearity embedded in the nonlinear shell. But you could also represent it as strut and tie model, and the struts and ties modeled as nonlinear elements. So once again, the capture of the nonlinearity in large structures can be approximated by a truss, nonlinear truss elements, which is more clear to visualize than the nonlinearity embedded in shell or solid elements. Last topic for today is extraction of this strut and tie model from finite element method. Because most of the time, people are now fond of using finite element. So finite element can be used, both shell and solid, to find out the strut and ties. So basically, you run the finite element model, you find the principal directions, and based on the principal direction of stresses, then you try to find where these struts and ties will be, which I've shown you already. So you could do this one. You do the finite element modeling, you find the stresses, stress direction, then you combine them to the min, F min, and F max, and then you get the strut and tie model from there. That's the way that many people are writing the programs to do automatic stress and strut and tie extraction from finite element meshes. And same thing here, for a beam, for example, of different, you can get the direction of the principal stresses, which can lead you to the formation of the strut and tie. And this is, once again, same thing. You can go further if you mesh it in very fine, and you can actually find these struts and ties more reliably from that. And you can go on to solve more complex structures like this one here. And if you do this one nonlinear, then you can do a lot more stuff. And there are software out there which are now doing it in that way. So it's the strut and tie model concept is coming back with nonlinearity in it now. So let's close this topic now. I think I just want to mention that strut and tie models and mechanisms provide a visual and conceptual flow of internal forces. So there's no ambiguity. We know what we're doing. We are the one who are making the internal stress transfer, and we follow it through all the way to details, reinforcement details. So we set up the model, analyze it, check it, and follow it. And then we use the compression capacity of concrete and tension capacity of reinforcement in efficient ways. And by defining such models is a load bound, we are ensuring safety, although we have to check the serviceability. The thing to remember is that transfer mechanisms are direction dependent. So if the point load is down, it's a different way. If it's up, it's a reversal of the strut and ties, as you know. So in some cases, for the load reversal, we have to consider both strut and ties alternating, like joints and like masonry walls. And serviceability checks need to be performed separately. So I think with that, we come to the end. Thank you so much, everyone.